Starting. All attendees are in listen-only mode.
Hello, everyone. Welcome to our webinar. I'm Andrea Velasquez, Global Marketing Program Manager for Analysis Solutions at Hexagon PPM. Today, our webinar topic is leveraging CAESAR 2 and FEA tools. Our speaker today is Tony Pollan with help from Willie Locke and Richard A. Tony Pollan has dedicated his life to creating and helping engineers apply the best and most advanced technology to the fields of piping and pressure vessel design and analysis. In 1991, he founded Pollan Research Group, PRG, to develop FEA-based software programs for use in the PV and P sector. Under Tony Pollan's direction, PRG performs consulting, training, and physical lab testing to confirm both the software's accuracy and usability. He regularly presents papers and findings at industry seminars and conferences. A quick reminder, all attendees are muted by default, so we encourage you to type your questions or comments in the questions tab. And now to our presentation.
There are a lot of new features in FEA Tools version 4.2 and CAESAR version 12 that's in production now in Huntsville. We'll talk about a few of the basic free features that were added that we think you can use every day. First will be the automated pipe shoe design, then flange load and tolerance guidance. Then Willie Locke will show how the new output processor can be used to run CAESAR models, compare results from multiple jobs, and solve nozzle load problems. PRG will be continuing to provide a collection of short presentations on topics like buckling, fitness for service and pipe components and bar supports. Please stay tuned to the latest on the PRG and Hexagon websites. Please note that all you have to do to get access to any of these free features that are delivered on the CAESAR 2 disk is when you're installing CAESAR version 12 and the Install Shield asks you to optionally install FEA Tools Essential, all you have to do is click yes, and then everything that we look at today will be installed on your computer with CAESAR version 12. B31J was released in 2017. Since that time, CIF, K, and SSI development for different components has continued, like pipe supports. Many of those calculations are available in some form in FEA Tools model conversions, available from this button. Here, this button is used to get free access to B31J and improved bend CIFs and Ks for attached straight pipe lengths and ovalization. Advanced pipe shoe modeling is also available from this button and is free to the translator and CAESAR user. As long as you're current on your CAESAR updates, access to this button is free. This button lets you read in point clouds and compare them to CAESAR models to make sure that supports, valves, etc. are entered correctly. This is free, and when you have a point cloud, it is very graphically informative. This same button also gives you a free ability to compare CAESAR models to see how the results from different versions of the same or similar geometries compare. Willie will use this tool to bring in CAESAR models, run CAESAR models, filter results, and compare the multiple models at the same time. These buttons let you quickly check flange locations using simple rules of thumb to see if problem areas appear due to bolt-up tolerances or operating overloading. If you have locations where you think you might have problems, then the exact loads that are developed can be used to further evaluate the flange. This is what we're going to look at first. We'll bring in CAESAR models to design pipe shoes for each automatically identified location and write a report detailing the design to make sure that shoes aren't overloaded and that what was picked for support location is adequate. So I'd like to talk for a moment about pipe support problems. Most pipe supports don't have any problems. Corrosion, coatings, these are all major issues when there are problems, but operators and manufacturers should discuss coatings and corrosion for their location and application before the shoes are installed. Today we're going to address overloads and design, which fortunately aren't too common. Here are typical corrosion problems at supports. This is courtesy of Piping Technology and Products. Here's some overloaded supports. And here's a test model that PRG ran in the lab to investigate the effect of pads, lugs, shoes, and thin wall attachments. When we think about pipe shoe design, the capacity of the shoe itself is usually given a cursory look based on catalog data. Then the load in the steel is checked in detail because that's what the structural engineer or the support engineer is most familiar with. The local stress on the pipe, that's not looked at very closely because one, it doesn't usually need to be, and because the structural engineer usually isn't very experienced with local loads on pipe. There is an MDC Project 15987, now 182625, that should be available to help with this shortly. In the few cases where high restraint loads, due mainly to thermal expansion, slip through the experience filter of the checker that we use now, problems can exist though. What we want to do is catch these problems before they impact the project or before they make it to the field. We would like to help the structural engineer or the support engineer check that he's gotten the support loads correct and that he's buying the right supports for each point in the piping system. There are a variety of pipe shoe sections, slide plates, coatings, etc. Simple T or plate supports are the most common, but stronger supports are available as needed. Pipe shoes can be welded or clamped, usually depending on the spec or the client preference. Welded and clamped shoes are usually split 50-50. As the capacity increases, so generally does the cost. The range of application of the manufacturer's pipe shoe catalog is one of the properties we look at when we're comparing manufacturers' designs. The broader the range, the easier it is to select consistent and inexpensive supports. Your pipe support provider should be someone that you talk to at least a little bit. They want your project to work. So what we're going to suggest is that when you're finished with any Caesar 2 job that has pipe shoes in it, and before you write the final report, you run the pipe shoe design wizard to make sure there aren't any accidentally overloaded supports. It only takes a few minutes, as we'll see, and it's free to do. When you're happy with the report yourself, you can hand the pipe shoe wizard output to the structural engineer so that he can check that what he's providing is what is suggested. If there's a difference, then some additional checking should probably be done. So let's quickly see how this works. The job we've been given to check is X049-A2. The first thing we want to do is start Caesar 2. It's here. I open Desktop XV Gas Transfer. Here's the job I was given. You can see the model. So we're just going to bring it in to perform an analysis on it. Here's the model. So we'll click on the running guy, and the model shows up with no locations that are overstressed. So we're finished with Caesar. We come to FEA Tools, and we want to run the pipe shoe design wizard. Got to find the same Caesar job in the desktop. There's our model. And there's our piping system. The first thing the software does is identify all likely pipe shoe positions. There are 97 of those in this model. So here's all the descriptions. So we can turn these on or off if we want to. Generally, these selections are fairly accurate, so you leave them on. Next, I'm going to tell the restraint designer that I'm only interested in clamped supports. By default, it will design both welded and clamped pipe shoes for us, but we're only interested in clamped shoes for this model. That's what the owner prefers. That's all we need to change in the design algorithm, and we press the Design Analyze button. This will take about 30 seconds, or less than 30 seconds. And here's the report. There are 4 out-of-range cases. These are supports on nodes that are outside of the catalog diameter limits for standard figure 98, figure 100, or figure 400 pipe shoes. But most importantly, there are 0 overloaded clamped shoes. Here are all the clamps that were needed and their design cases. And then when we get down into the body of the report, this is what the structural engineer would be interested in for all the supports in the model. So this will help the structural engineer make sure that he's selected the right support for each location. From a purely checking point of view, you'll notice that there's a graphical output at the top. So if we're not interested in boring down into the details of the numbers, once we've made the run, we can come straight to the graphical output. This shows all the cases for all the support points in the model. So what we can see is that some of them are close to what we would consider the design allowable, but the majority of them aren't. We can hover over those supports to find the node numbers that we might want to take a look at. So let's see how this works in a typical design setting where you want to check someone else's work. So you open their piping file. So they've given you the job names, the Caesar 2 file that they've run and that satisfies the code requirements. So you bring the model in. Pretty good size model. There's 167 different supports and guides and limit stops in this. All of them have been picked as pipe shoe locations. Say design and analyze. The allowable loads tend to be on the conservative side, so as long as we're under the allowable loads, we're generally pretty happy. Even if they're not pipe shoes per se, they do give us a pretty good indication of the allowable load limits of the piping system. So the model finishes. These are the 2 numbers we're principally looking for. You'll notice I didn't ask for either welded or clamped shoes in this design, so it sized them both. Neither welded or clamped shoes would be overloaded. Principally interested in a quick evaluation. Everything is just under the allowables. Again, the allowables are usually pretty conservative for pipe shoe loads, so this is more than likely okay. If you were a little bit concerned about overloading, you could come in and take a look at these nodes. So in 30 seconds, that's literally how Caesar models can quickly be checked for all the pipe support locations in a fairly good sized Caesar model. So now we've seen how the pipe shoe design wizard works. I'd like to make a few additional brief comments about pipe supports and their design. To start with a pretty poor analogy, buying most pipe supports is as simple as buying a loaf of bread, but some pipe supports will absolutely require more attention, and other pipe supports are more like finely designed machines. In most cases, you'll find that you can work with a support manufacturer who has the capability to provide any level of support. What we're doing automatically with the pipe shoe wizard is closer to buying a simple loaf of bread. But what we're doing is making sure that you're getting the best quality bread for every sandwich, you and everyone else on your block, in 30 seconds. For more sophisticated support designs, please do not rely on an automated evaluation tool. The pipe shoe wizard is not intended to turn an average designer into Leonardo da Vinci, but it should help everyone avoid mistakes. To quickly continue this analogy, once you know what bread you want, you can buy the bread from a thrift shop on the corner or a fancy supermall. But at some point, you may need scalable support services for all of the things besides the bread that you need. Also, at some point when you want to contact the vendor, you need to call on their experience. Companies like Piping Technology and Products, Leasiga, are household names that are known for supporting their clients and that have been supporting them each for more than 30 years. The short story is that simple supports may not be so much of a problem, but when the level of difficulty becomes greater, a good contact with someone like PTP can be very beneficial, and those folks are there to help. Email and the phone to get a hold of their expertise is the way to put more eyeballs on a problem, and that will result in fewer mistakes. So now let's take a similar look at checking flange load. What's the difference between what we're getting ready to talk about and what most pipe flange checkers do? Most pipe stress flange check routines read the Caesar model, pull off the loads at flange locations, and tell you if they think those loads are too high based on some set of criteria or rules. We're going to do that too, but we're also going to do something else, which is the reason this tool was written. What we're going to do is take the set of equations that describe the entire piping system in the C2 model and condense it down to just the flange degrees of freedom for each flange in the model. The matrix K flange here represents the entire piping system surrounding the flange. If it's a flange in the middle of a piping system, then K flange is 12 by 12 for 6 degree of freedom piping systems. If K flange is at the end of a piping system, a pump nozzle for example, then K flange is a 6 by 6 set of equations. With these relationships, we can superimpose the flange matchup tolerances that you specify or that we take from PCC1 and determine the loads if the flange is bolted up with those gaps or tolerances. The result is stresses based on gap closures, stresses based on operating loads from the Caesar 2 file, condensed stiffness matrices, and precise loads for all of the flanges in the model that you select based on gap closure and operating loads. To make the process as quick as possible, we recommend simple rules of thumb applied to the stresses to make sure that a flange doesn't end up at a point in the system where the loads are excessive. This is just asking for trouble. We're not trying to turn anyone into a flange Da Vinci, but we hope this tool helps everyone quickly and easily identify what might be a mistake so that you know when you maybe need to call your company's Flange Da Vinci. So let's see how this works. So we start with FEA tools. Essentials on the right, the advanced version on the left. Both versions have a flange condensed processor. Here's the form for the processor. Select a job name. Any C2 file, it can have been run or not. Once we bring the model in, we hover over all nodes or turn that mode on so that we can find the flanges in the model or the places where we would like to investigate potential flange locations. If flanges occur at high bending moment locations, then we'd like to find places in the model where there are lower moments. And so you can pick literally any node in the model to have a flange calculation performed for that node. So we're just stepping through the model, identifying each of the present flanges. Once the flanges are entered, we select a multiple flange option and enter their values. If we want to put in allowable loads or gaps, we can here. If we don't put in any gaps or tolerances, then the software will calculate them based on the pipe diameter from the guidance in PCC1. When the nodes are entered, we press the Perform Condensation button. Condensation of this system takes about 10 minutes, 5 to 10 minutes. The system is performing condensations twice for flanges that are internal to the piping system. So it steps through each of the nodes where flanges are located. And when it's finished, stress plots appear. These plots show the maximum operating stresses in the pipe adjacent to the flanges and the maximum stresses due to gap closure. Here we can see straight away that 500 has got an exceedingly high stress, way over what can be considered any normal allowable. And the rest of the flanges are all within reason in terms of flanges in pipe that's highly stressed. We can look at the stresses just due to gaps, and here we see that a few of the flanges in this model are sensitive to tolerance closures. If the gaps in PCC1 are present at this flange when they bolt it up, the loads in the flange will be a little high. These other flanges, even if the tolerances are present, the loads will be fairly low. There's also the tabular report we talked about. If more detailed and accurate results concerning loads are needed, here each of the flanges and the data associated with it is listed. Stiffness and flexibility matrices for each flange are printed, along with the calculated loads to close gaps and from the maximum operating loads in the Caesar model. With a very quick exercise, we can hopefully help spot locations where flanges should either be moved or potentially protected from excessive bending moments. So as long as when you're installing Caesar version 12, you say yes to including the FEA Tools Essentials You will have access to mim out the point clouds and all of the administrative tools that Willie is about to go through now. Willie?
Thank you, Tony. We will use the mim-out output processor not only to post-process the CSR2 output, but to go through the engineering process of solving an overstressed model. So with that, I'm going to open the output processor, which is part of the Essentials version and the Advanced version. I can use the recently opened files if I had opened it before, or I could go to Add Open Piping Models. And I'm going to select my original one. And I'm going to hit Open. Now, once I open my model, I can see that I have some overstress in different load cases. I have 40 load cases here, and I'm overstressed in sustained cases and 2 occasional cases. So I'm going to go to the first overstressed load case, and I'm going to find out what node number I'm overstressed in. So I'm going to sort descending, and I'm going to see a 1650 and 1150 are overstressed. I want to find out where these node numbers are in the model. So I'm going to go to plots on point clouds. I'm going to try to find the overstressed nodes using the find feature in the output processor. I'm going to click the search, and I'm going to hit all nodes. I'm going to deselect all of them and find 1650. So I'm going to filter on, and that gives me everything that contains a 1650. So this is the one that I'm interested in, and then also 1150. And press enter, and I find these 2 branch connections are overstressed. Looking at the overstressed nodes, I can see that there is a sustained stress index that's over 1. A sustained stress index, since this is a sustained case. I want to see if I can reduce this sustained stress indices by changing the t-type. Without going back into the input, the CSR2 input, I can go into File and go to View Input. Clicking on SIFs and Ts, I can see that 1150 and 1650 are both welding Ts. The best solution from now on would be to run finite element analysis through the CSR2 FEA translator. So now I'm going to open the CSR2 translator, and load my model. Now the model is loaded, and I can decide where to get the stress intensification factors from, FEA or B31J. ASME B31J is part of the Essentials version. FEA is part of the Advanced version of FEA tools. So I'm going to pick FEA and press Convert. I want to replace, I will say yes. Now the model has translated, and I have not run this through Caesar, but I'm not going to do that now. So I'm going to go and add the FEA version. So now I'm going to click and I hit on open. Notice that I haven't run the Caesar model. It will tell me that the model has not been analyzed, that there's no output for it, so I want to say yes to analyze the model. This will run through CSR2 and then load the results into the output processor automatically. Now both models have loaded. If I collapse the tree view, I can see I have the original model and the translated model. So if I expand the translated model, we have solved the problem with the sustained cases. But we do have occasional cases that now are overstressed, the distribution of loads around the model due to the improved flexibilities and SIFs have shifted the stresses into different locations, which now have overloaded the occasional cases. Now I want to find out which are the nodes that are overstressed for these cases. And again, I'm going to sort descending and see what 858 is. So now I want to filter through those nodes so since now I'm only interested in the nodes that are overstressed. So I'm going to go to filter and select none, and I'm going to find 858 and filter on and exit. After filtering, I'm going to go to the highest load case, the highest percentage load case, and I'm going to see that 858 and 859 are overstressed, and these also have sieves. I want to find out if this is a bend or an intersection. So I'm going to go back to the plots and go to the FEA model. I'm going to collapse the original model and go to the FEA model and go to the highest stress case, and I'm going to press go. Now I'm going to try to find where 858 and 859, and again I'm going to use the filter option, hit all nodes, select none, and 858 and filter on. So this is where 858 is, and where is 859, since both of those are overstressed. 859 is, there are two bends in this location, so these are overstressed, and now I want to find out why these are overstressed and this second one isn't. I'm going to close this. Now I'm going to go to labels and select restraints. There's a restraint at 1190, at 1230 and 1240, but there isn't one in this location, so I just realized that I forgot to add restraints. This is why my bend is overstressed. So now I have to go back into the Caesar model and add those restraints at these locations. Now I'm going to open Caesar version 12. I'm going to open my FEA model, since this is the one that we're modifying now. The first thing to do is I'm going to save the model as. I'm going to save it with a different name, since I'm going to make modifications to this model. So I'm going to click FEA-2 and save. So now I have added my restraints, and all I need to do is save the model and close it. Close Caesar 2. Then I'm going to load this new model. So this is FEA2, and I press open. Once again, I'm going to run through Caesar within the output processor. The model has loaded. If I collapse the first one, we'll notice that there are 3 loaded, and that the third one has no overstress. I'm going to expand this case. Notice that the filters remain applied for that given node. Load case 31, which was the highest case before, and I'll see that there is no overstress. We're at 56% and 47% for nodes 858 and 859. Now I want to make sure, I want to see how all these stresses compare to each other. I'm going to clear the filter because I want to see the entire set of stresses. I'm going to say filter off and apply and exit. So if I click on code, this is every stress in the model. There's the blue line is the original model, the yellow line is the FEA, and the red line is the ones with the correct restraints on. We notice that there's overstress in the occasional cases here in the original model. You can filter each of these cases as needed. So if you right click and click on filter, you can filter several ways. First, you can filter by only occasional cases by typing occasional, or you can type the load case numbers, or 5 through 10, and it will give you those cases. You can also filter by operator, which will, as if you want anything that's greater than 5, load case number 5. So this can be done by load case, or it can be done by percent of allowable. In this case, you will want to see anything that's greater than 100%. So you filter that, press filter, and it will show you just those that are over 100%. The same can be done for the second one, and again greater than 100%. Okay, and in this case there should be no nodes that are greater than 100%. So nothing forced. So in the original model, we have 4 nodes that are over 100%, and we can see which one these are. In the FEA model, we have only 2, and in the third model, we have nothing, since this is the case that we are going to use. Now that we have solved the overstress, we need to make sure that the loads on the heat exchangers, which are these right here, are not overstressed or overloaded based on allowable loads given from the vessel engineer who run Nozzle Pro and gave us the allowable loads. So now I'm going to go to filter and find 9620 find. So these are my restraint nodes now for the heat exchanger nozzles. I'm going to see the restraint loads for all combined models. Notice how the restraint loads have changed due to the difference in stiffnesses and boundary conditions. These are for every combined model, for all the models for these specific nodes, and you can do that individually as well. So this is MR and FR for forces, for resultant forces. I want to see in specific load cases. For the third case, I'm going to uncheck beam stresses. I want to see restraint nodes. So that's MR for this specific case. And if I keep clicking on different cases, I will see that for a specific load case. So now I want to find out if these resultant moments, or in the specific MX and Y and MC direction, if these are over the allowable loads given from Nozzle Pro. So there are two options here. First, I can look at the moments in the MX direction, MY and MC, and try to convert those into in-plane, out-plane, or torsional moments. And that could be error prone, especially if I want to do it for nozzles that are in different orientations. The easiest way of doing this is to go back to Caesar 2 translator. I'm going to load my FEA-2 because this is the one I want to use. So then the model has loaded, I'm going to press show advanced data and go to the supports and nozzles tab. I'm going to press on plus, and I'm going to say that this is a nozzle. I'm going to find the Nozzle Pro model that I was handed that has the model analyzed. So the model name is Exchanger Nozzles. I'm going to press open. Original model loaded, the -FEA-2. For every node and every load case, there's the forces and the moments compared to the Nozzle Pro allowable loads, which are down here in the second line. So every load case has been analyzed, and the maximum cumulative damage is shown on the right. We scroll down for this particular node. There's the maximum percentage for every load case. So we can see that the maximum here is 51. We can look at this in a tabular form, which might take a little longer, or we can look at this in a graphical form. Clicking on reaction load plot, we can see that none of the cumulative damage percentage is over the 100% maximum. Now, as a final check, I want to compare all three models. So I'm going to go back to the output processor and go to the comparison tab. This tab will show only when there is more than one model loaded at the same time. So now I'm going to press finish and compare. Note that the filter applies to all of the tabs here except the 3D plots. But the comparison also has filtered nodes, so I will only see the vessel nozzles here on the tables. The left hand side as they were entered in the model. The right hand side is sorted by highest displacement difference to lowest. Now I have removed the other two models. I'm going to go into the PDF reporting and select MIM report, which is the recommended report. This will select the appropriate load cases and the plots to be exported into a PDF report. So now press export. Once a report is generated, every table is going to be printed out into the PDF report that can be sent out to the client or printed out. Thank you.
Thank you, Willie. There's definitely a lot going on many technological fronts. Certainly with the buckling behavior of large diameter pipes and vessels, with the code equations that address the behavior of these large diameter pipes. Nozzle Pro includes updates, for example, that simulate fabrication perturbations that can result in minimum buckling loads, buckling and wrinkling of large T's in compressive bending states in D over T ranges less than 100. With new analytical tools, we're testing geometries for SIFs and SSIs that are larger than components that have ever been tested previously. Each of these issues is included in some manner in the new Nozzle Pro and FEA Tools advanced versions. We recognize that more examples and easy access virtual walk-in sessions are an essential part of spreading and adjusting technology for the needs of the user. PRG and Hexagon will continue to provide a wide variety of information, new examples, and walk-in sessions so that new users can become accustomed to the concepts and the technology, and so that older users can verify quantitatively and analytically what they've assumed for years. Please stay tuned to PRG and Hexagon websites for more information about upcoming Caesar, FEA Tools, and Nozzle Pro versions, trainings, and examples. We would like to thank Hexagon for their assistance in producing this webinar, Piping Technology and Products for photographs and support, and to everybody in attendance for your time. Thank you.
Thank you, Tony. And now we will have a Q&A section by Richard A.
Okay, so we have quite a few questions, Tony. The first one, before I start, I'd like to say, if you didn't see my answer earlier, any question that is not answered in this verbal section right now will be addressed in email and sent to all attendees in a few days. First question, do you have a chart or table comparing SIS and SSIs to compare against a generic 0.75 code factor?
Tony, you're mute.
Tony, did you hear that? Willie, maybe you can answer that one.
Yes, we do have a comparison in the Caesar 2 FEA translator. Once you run a quick translation, it will give you the comparison from B31.3 SSI 0.75 times small I against B31J and FEA.
There's also a panel on Nozzle Pro and the FEA Tools that lets you bring up a spreadsheet, and you can put in any intersection you like, and it will compute the SIFs and the SSIs for both branch connections and bends, and you can see the comparison of the new data versus the old data.
Okay. Here's a question. ASME B31J transformation is applicable for lateral T's as well?
For laterals, the B31J has a note that states that the stress intensification factors are good for the that are present in B31J as they are good for in plane and out of plane loads through the branch, but not for torsion. For torsion with laterals, you've got a wider, thinner footprint, and B31J was not designed for that. The SIFs in B31J were not designed for that. So that's, as long as you've got in plane and out of plane loads, what's there is adequate.
What about the FEA option on the full version?
That'll work every time.
Okay, perfect. Do you offer analysis options for support locations not on shoes, particularly when point loading, say, round bars involved?
Yes, there's a cumulative damage tool that provides a variety of ancillary calculations for pipe. So if a person has a Caesar model with a support at a given location, you can pull up the cumulative damage tool, go into local loadings, and tell it that you've got a bar support. Interestingly, that was developed for bar supports with corrosion, because a lot of bar supports develop corrosion under the bar. So you can check the bar support as new, and you can also check the bar support with various sizes of corrosion between the bar and the pipe.
Okay, great. Is it possible to customize the shoe design wizard based on custom supports?
Willie, can you answer that?
Yes, you can. The custom supports will have to be built in NozzlePro, and those can be used for analysis type in the pipe shoe design wizard. So we would compare the restraining loads from the Caesar model against the allowable loads built from the NozzlePro model that's custom.
Okay, great.
We do have some customers that build their own libraries of pipe supports. When they have specialty pipe supports, different allowables, different wall thicknesses, they can design them any way they want. And then when they go to select pipe shoes, they can select from their own personal library.
Okay, perfect. Are you going to include catalogs from companies other than PTP, or is this the default reference for this tool?
It's certainly the default reference. We've worked very closely with them to make sure that the loads and allowables are computed properly for clamps and local supports. But just like we did, Rich, in the early days with springs, there's a point where if someone else wants to participate, we want to be transparent and work with anybody that wants to provide a value to the user.
Okay. Are we using the same allowable as B31.3 for comparing pipe shoes?
Willie, do you want to address that?
Well, the allowable loads for the pipe shoes are obtained from final element analysis, and we compare what the wizard does is compare the restraint loads against the allowables from NozzlePro. I hope I answered that.
And I think the concern is that what is the stress allowable in the pipe? And so, because there's three things that have to be checked. There's the shoe that has to be checked, the steel, which we don't look at obviously, but we look at the stresses in the pipe shoe, then the stresses in the pipe. And when the pipe gets hotter, the allowable goes down. So there's, I believe, 2 allowables now, because most allowables for pipe shoes up to 500 degrees can be grouped in either the 20,000 PSI allowable or the 15,000 PSI allowable. So there's 2 groups of allowables that can be chosen from if you've got hot pipe. And anything over 500, I think 500, maybe 600 degrees, I forget the exact thermal cutoff, you need to be more careful with. That's where you would develop your own library, for example.
Okay. How do you establish the axial stiffness in a clamp support?
That's a great question. Basically, what you assume is that the clamp clearly surrounds the pipe and that the bolt loads control the allowable loads. The stiffness is designed, the stiffness that's used is intended to replicate the condition where the bolts hold the clamp tight enough so that there's no relative movement between the pipe and the clamp. And so we put the stiffness of the clamp included in the finite element model, and then check to make sure that torsion loads and axial loads don't produce enough load to cause the pipe to slip through the clamp. And if that's done, then the other assumptions about clamps and stiffnesses are valid.
Okay. Shoe lateral and axial capacities were supplied by PTP or determined by PRG?
determined by PRG, actually determined by a nozzle pro finite element analysis. All of the pipe shoes for all of the wall thicknesses for all of the diameters, Willie and his group ran, and those are all stored in the PTP library.
Okay. Does the software check if the clamp will fail or not, or does it check only shoe and clamp support?
It checks the local stress in the clamp, and it checks the local stress in the pipe. You can imagine if you have 10S stainless steel, the clamps will be thicker in some cases, most cases, than the pipe. So the stress moves to the pipe. When you've got high bending moments, if you've got a pipe shoe that's used as an anchor or some guides in limit stops, those will put high stresses in the pipe rather than the pipe shoe.
Okay. Does the SIF calculation from the FEA translator consider corrosion allowance?
That's a great question, and the answer is no, because the interpretation is that it's not supposed to. The SIFs, the test for SIFs, and the calculation for SIFs all use nominal wall pipe. The inclusion of the corrosion is made at the post-processing level of the stress analysis when you use a corroded section modulus. And then it's that corroded section modulus that increases the stress due to corrosion.
Okay, I think that one was just answered. Can this program be used to investigate the possibility of elastic follow-up in a piping system?
The elastic follow-up problem is let's say if the elastic follow-up occurs at a branch connection, then with Nozzle Pro, you can run the nonlinear calculator to see if you're reaching a point where you don't provide, let's say, a linearized load. As we know, there's local overstrain allowed in piping components, so it's plasticity. But just because you hit a plastic level in a branch connection or a reducer or even an elbow, that doesn't mean that you lose capacity of the component. So you can reach a plastic limit and keep loading, and globally the component behaves as if it's elastic, even though it's got local plasticity. So in those cases, elastic follow-up really doesn't occur. It's not defined in those cases per se. What happens in the Nozzle Pro run is as you continue to load it, you see that eventually the load capacity changes. And it's then when the load capacity changes that all the elastic energy from the surrounding system goes to that component. And that's when you have elastic follow-up. So with a little bit of awareness and an interaction and making nonlinear runs of the component using Nozzle Pro, I would say, yes, you can evaluate the elastic follow-up in components that are analyzed.
Okay. Shoes that have a saddle on top can be modeled here.
Saddle on top. Saddle on top. It's interesting. Willie, will you pick those out automatically, or I guess the user can certainly put one to the